This is Group 17's final presentation. Our idea is the personal wardrobe assistant. I'm O'Neill Thomas, the project manager, and I'm an undergraduate in computer engineering.
So I'm Juan Herrera, computer engineer.
I'm Efren Cintron, electrical engineering.
And I'm Maximilian Carroll, electrical engineering. So we will start with motivations. What we really wanted to do is we wanted to expand the automation process and focus on a aspect of our lives that really hadn't been touched by this technology, which is how we came to the idea of inventory management of clothing. We also wanted to create a project where everyone could really work on something they enjoyed. And at the end of the day, we just wanted to make our lives easier. And we believe this project will accomplish this task.
So we have some goals and objectives for our project, and I'll start down the list. The first goal, learn and apply concepts of radio frequency technology, power supplies, and microcontroller communications, and developing a full stack application. Second, to build a system that will track a person's clothing inventory with precision. And third, help average people save time dealing with articles of clothing. And lastly, and most importantly, completing our undergraduate careers as electrical and computer engineering students. So here are some specifications for our personal wardrobe assistant and also some demonstratables. I'll just go ahead and pick some out of the list. The first one is a passive low frequency scanner of 5 to 10 centimeters. Our personal wardrobe assistant also needs to be able to connect to Wi-Fi, and our personal wardrobe assistant will implement a MERN stack, and that will be contributed to our full stack web application. And we'll also be using a RFID reader and LCD screen that will draw 86 milliamps. So some demonstratables for our personal wardrobe assistant is 5 centimeter range on the antenna, 5 to 10 centimeter range on the antenna, and also scanning in wardrobe items and scanning out wardrobe items.
Some of the challenges that we face this semester are COVID-19 pandemic. We pretty much start Senior Design 1 virtually as Senior Design 2, making less contact with the members of our group to do in-person meetings. A limited budget of no more than $400, which is equivalent to $100 for each member. Equipment to perform testing our hardware. We went to campus a couple of times to do some testing and soldering. We've been doing virtual meetings on Discord to chat and work with our project. And the biggest challenge that we had is the PCB fulfillment. It took around 3 different versions to get one that properly works. In terms of the distribution workload, we have O'Neill Thomas, which is our team leader. He works with the microcontroller, Wi-Fi model research and part selection, programming, and PCB design. Then we have Maximilian Carroll, which is another team member. He was in charge of the power supply design, regulation, and PCB design. Then myself, Efren Cintron, also a team member. I was in charge of the RFID research and part selection, antenna design and tuning, and the PCB soldering. And lastly, we got Juan Herrera, also a team member, which is in charge of the software, in this case with the full stack web application development.
For the first major process in our design, we had to choose an AIDC system. And the two of the major ones we considered were RFID or barcode. And both of these have advantages and disadvantages. For example, an RFID can scan multiple tags simultaneously, but they're also more expensive and more complex than barcodes. Barcodes, on the other hand, are much smaller and lighter than RFID tags. ID tags are able to store just as much, are able to store less information. But the big reason we didn't choose barcodes is because they are not easily replaceable as RFID tags are. As stated before, we were really deciding between the two AIDC systems, or automatic identification data technologies, and we decided to go with an RFID system. The three major components of an RFID system are the scanning antenna, the RFID tag, and the RFID reader. We decided to go with a passive RFID tag with a frequency of about 125 kilohertz. They are able to store large amounts of information, and they're very easily replaceable when damaged, and that is the main reason we decided to go with an RFID system. For the next, we had to decide if the power source on our project was going to be AC or DC, and there are advantages and disadvantages to both. For example, an AC system requires more components to convert from AC to DC. It's more complex and more expensive, and it is location dependent, and because it needs to be close to a wall to a power socket on a wall. A DC source is easier to troubleshoot because of the relative simplicity compared to an AC system, offers greater mobility for the project, but sadly, once the batteries are drained, you either have to replace them or recharge them. So what we ended up going with was a DC system largely because of the greater mobility for the project. All the electronic components on the PCB require DC power anyway, so we wanted to focus on that. And finally, it is very easy to replace. Nice. We decided to go with two separate battery sources for this. One, we had 8 AA batteries. We connected them in series to produce about 12 volts. 12 volts in these, and this power source is responsible for powering the reader, the LCD, and indirectly the antenna. Then we also have a lithium-ion battery, which is solely responsible for powering the microcontroller. For the actual power regulation circuit, we decided to go with a 7805 voltage regulator, which will take the 12 volts DC and convert it into 5 volts DC output. Now, the main reason we decided to go with the L7805 was because it was recommended in the data sheet for the RFID reader. It is the most common form of powering this specific device. And the other options were considered, like basic voltage divider, Zener regulator, or even a step-down regulator. But after researching, voltage and Zener regulators are not designed to properly power components. And again, the main reason we chose this one is because it's just recommended in the data sheet. We also have other parts to the power PCB, like for example, A1 and 4001 diode to regulate current and protect against overvoltage. And then we have 2 smoothing capacitors to improve the voltage output and also add stability to the circuit. Now, despite having our PCB working, a stretch goal for this project is to create an AC power source actually, so that the users wouldn't have to worry about replacing batteries and stuff like that. And the 2 major components we would have to add in order for this to work are 1, a transformer, which would step down the AC voltage, let's say 120 to a smaller, like 12 AC. And then this AC voltage would go into a full bridge rectifier as seen in the bottom right, and from there it will go into a DC regulation circuit. Also, we were going to make a second version of the project that is much smaller and more compact, that would only require between 3.3 and 3.6 volts to operate. For this, we would use a LM317T and a test circuit of the specified DC regulator is seen in the bottom left.
For the hardware selection RFID reader, we narrowed it down to 3 different ones, and we ended up going with the ID3LA since it gives us the ability to build out an antenna with longer range. The ID20LA and the EM18 has an antenna integrated, and therefore the reading distance is fixed. The ID3LA reader acts like a transceiver, receiving the tag ID from the antenna and transmitting the information to the microcontroller. It's Arduino I2C compatible using pin D0 that will communicate with the microcontroller. It's energy efficient, consumes around 23 milliwatts of power, and is easy to set up. The RFID antenna is crucial for this project and performs 2 important functions. It transmits power to the RFID tags and receives data back from the activated tags. The passive tags wait for a signal from the RFID reader, and this sends energy to the antenna, which converts that energy into an RF wave that is sent into the read zone. Once the tag is read within the read zone, the RFID tag's internal antenna draws in energy from the RF waves. The specifications of our antenna is 125 kilohertz. Since we are using low frequency passive tags, that requires this frequency to be able to read it. A range from 5 to 10 centimeters is desirable so the user can scan the RFID tag without the need to be so close of the RFID antenna. And a compact size antenna that will increase the field strength and coupling in order to avoid any interference. The materials used to build out the antenna are PVC tubes of 2, 3, and 4 inches of diameter. Also, a 28, 30, and 32 AWG copper wires. These copper wires are coated with a thin layer of insulated enamel that prevents any short circuits when cable is coiled. Having these materials in hand, it was time to build some RFID antenna. The combination of having 3 PVC tubes and 3 different copper wires give us a total of 9 antennas. In order to know how many turns each antenna needs, a multi-layer inductor calculator was used from www.circuits.dk, which we input the inductance of 1.337 millihenries, the wire gauge in terms of AWG, and the PVC tube diameter in millimeters. After getting those values for each of the antennas, the copper wire was winded tight to produce better results. Then I burned the insulation of the 2 ends of the wire and soldered a 24 gauge wire that fit better into a breadboard. To test each antenna, the MSP430FR6989 was used as a power source to provide a voltage of 5 volts. Connected to the breadboard are the RFID reader and the SparkFun RFID starter kit. The 2 ends of the antenna are connected to the pins 3 and 4 of the RFID reader that sits on top of the SparkFun kit. This kit has a buzzer that makes a sound when the tag is detected, without the need to use Arduino or any kind of software. The table on the left represents the antenna with no tuning. 7 out of the 9 antennas were able to read the tags. On the right corner of the table, show us if the waveform expands or compresses. When the waveform on the oscilloscope expands, it means that it needs more inductance. Therefore, we need to wind more copper wire. When the waveform compresses, it has too much inductance and needs to take out some copper wire from the pipe. The table on the right shows the antennas to know. All of them improve the reading range, and the best one is highlighted in red. This antenna that we selected is in 2 inches diameter with a range of 8 centimeters, having a compact size and fulfills the range requirements.
All right, so time for the selection of the microcontroller. So for the microcontroller and testing our system, we decided to go with the Adafruit Feather Huzzah due to its small compact size and its being able to use I2C and UART communications in order to communicate with the LCD screen and the reader. The Adafruit is also compatible with the Arduino IDE, which uses C programming language, which made it easily programmable. The Adafruit Feather Huzzah is integrated with the ESP8266 Wi-Fi module, which will be used to send post requests to our remote database. Our other considerations of microcontrollers was the MSP430, the Arduino Uno, and the Raspberry Pi. And in the bottom left, we have a table showing the price ranges of each microcontroller. And the reason why we went with the Feather was because it was our cheapest option. Here is our first version of our PCB. So actually ordering and designing the PCB, it took 3 iterations in order to get a PCB to be able to be tested and operating. Here you can see the different parts of our PCB labeled. We have the power regulation, where the LCD is, the RFID reader, and the microcontroller. So we have a stretch goal, as Max stated earlier, and is to use a standalone Wi-Fi module, which will save a lot of space on the PCB and also save power, the power output of our device. And so for the standalone Wi-Fi module, we decided to go with the ESP10S, which allows us to completely exclude the Adafruit Feather and simply program it in order to communicate with the RFID reader and send out post request via the ESP8266 Wi-Fi module that is integrated onto this standalone chip. And on the left are some honorable mentions of Wi-Fi controllers that did not make it due to their lack of programmability and just being unavailable on the market. Here is version 2 of our PCB. So the size of our PCB has shrunken considerably due to not having the Adafruit Feather Huzzah on the board and the Wi-Fi module being so tiny. And we also decided to exclude the LCD because the Wi-Fi module was not able to communicate using I2C connections, which the LCD required. So we decided to opt out for an LED, which also works considerably well with our system. So we have an LCD and an LED and a buzzer integrated to for our user interaction. So for the LCD screen, we decided to go with a 16:2 LCD screen due to simplicity and space. There was no need to have a large LCD screen, for example, a 20:4. So we decided to go with the 16:2. We also decided to go with an active buzzer due to the fact that a passive buzzer would require a lot more work when it came to sending a signal to the buzzer. An active buzzer, all we need to do is send one logic signal, a high voltage to it, and tie the other end to ground, and we'll get a beep. And the same thing for the LED. The LED is quite simple to use. All we need to do is tie it to a high voltage and the other end to ground, and we'll get the LED to light up. Here is some pictures of our final product. On the top left is with the case on and the LCD screen attached to the case. And on the bottom right, we have the case off where you can see the PCB and the connection between the LCD and the antenna.
All right, so for the web application, we decided to implement a merge stack standing for MongoDB, Express, React, and Node.js. Mainly went with MongoDB due to its NoSQL database and effectively is very flexible and very easy to change on the fly. Also very high performing. The reason we went with React mainly was because Angular is way too complicated and I don't know TypeScript. And I picked React over Vue mainly because there's more documentation for React online. So for the backend server, so obviously we did a server using Node. When some of the main libraries we used were Express, Morgan, Helmet, Course, Mongoose, Bcrypt, and Multer. Express is just helps with routes and effectively helps with the entire API development. Morgan is a logger. Every time someone hits an API endpoint, it logs in the console. So we're able to keep track of who's hitting what endpoint and when. Helmet protects the headers, protects essentially against attacks. It keeps some of the headers hidden so they don't know what we're using on the backend. Course allows us to utilize the API from a different port. Obviously, this is helpful when you deploy the server to Heroku. Mongoose is an ODM library for MongoDB, allows us to use queries, searches, selects. It pretty much allows us to do anything we want to do with the MongoDB database. Bcrypt is used for hashing passwords, and Multer allows us to take in files. We have pictures in our database, but instead of storing the pictures inside the database, we store the path and we create a folder inside the server that stores all the users' pictures coming from the articles. So the structure for the database, we have one main schema. The schema has a user schema containing wardrobe data, article data, security, email data, and email data. This is how basically instead of having a table like you do in a SQL database, you have schemas in MongoDB, and everything is a single document. So you don't have to constantly create new views, create new selections like you do in a SQL database. You just have your one document and you interact with the one document. So for the front end, this is where it gets interesting. So the front end, we use React. Most specifically, we use React with JSX. Three of the main libraries used were Axe, which helps interact with the backend server by allowing us to do HTTP request from the front end. React Router DOM allows us to create routes and create links. So we're able to link our multiple pages. And React use state, use effect, and props. So React use state is essentially global variables. So when a page gets rendered in React, it's essentially a function, and that function renders out the page. Problem being, if you don't have global variables per se in that application, you have to use state variables. This is useful because every time we do an API endpoint call, whenever we click a button, whenever we open up a model, we want to keep track of those states. And to do that, we use state variables. This came in really helpful when I wanted to render out the articles or the wardrobe for the specific user without having to refresh the page. So every time I did that, I called this function called render out. It calls the API endpoint to log out all of the user's information, and all of the user's information is stored in multiple state variables that is used to render out the specific HTML element whenever we want. Lastly, we use session ID. So I try to use cookies. Cookies pretty much generated from the server and sent to the user's front end and stored. That way you can keep a session open. I couldn't get that to work. So what I ended up doing is I ended up sending as the user's ID and a time limit from the backend to the front end and storing that data locally. So none of the user's information is exposed apart from the ID that's generated by MongoDB and an integer that represents the amount of the session length. For the front end, we also use CSS, our own personal CSS, Bootstrap, and mostly Material UI. Material UI is a React library that gives us the ability to create HTML elements that are already customized. All we have to do is, let's say we put a grid, specify how many columns we want on the grid, the spacing on the grid, alignment on the grid, instead of having to do that by ourselves with our own CSS. And this is a simple representation of the website. That's the main page right here on the right. And on the left, we have the wardrobes and the articles that are represented inside the wardrobe. So like I said, I didn't want to refresh the page anytime the user wanted to select a different wardrobe, or when the user added an article or deleted an article or updated a wardrobe. Whenever the user clicks one of those buttons, the state it's saved after the end call, after the API call, and it's just re-rendered instead of refreshed.
So here's the first half of our budget table for the final project. And here's the second half of it, detailing all the parts and how much it costs. We came to a total cost of $315.16, below our budget of $400. And this is just a completion status list showing that everything is done.
All right. So in conclusion, the personal wardrobe assistant was designed to help the average person save time doing mundane tasks such as organizing and keeping track of their clothes. By using the personal wardrobe assistant, and the user will be able to understand what clothes are in their inventory and what clothes are out of their inventory, which will allow them to be able to see statistics and things of that nature. Overall, our group had a great time working on this project. It definitely showed us how a team is supposed to operate in order to get a job done, how if everybody plays their role, then we can actually come together and build something that actually works and somebody can actually use and utilize. And we'll be able to carry these experiences and these skills that we've developed into our workplaces as we move forward into our careers in either academia or into the industry as computer and electrical engineers. And yeah, so this project definitely showed us a lot about the experiences that that typical engineers will go through on a day-to-day basis, and we will definitely be learning a lot in our future when it comes to project development. Thank you.